All right. Just a couple of quick announcements. Monday, we'll have the second prelim just like we had the first. It's open book in-class exam. I think the topics would be everything till assignment 4, pretty much all the problems. So essentially, all the way to chapter 8, and then you saw we had one problem, chapter 9. I mean, it's kind of section 9.1, if you might. It would be something you should just read a little bit. And I'll do a review of the topics that are expected to be covered, and essentially it's a review also of the general topic of lasers as well. I think I believe repetition helps in seeing a bigger picture, but hopefully you see some newer connections. Those of you who have not picked up any of the old stuff, like either Prelim 1 graded exam, graded Prelim 1s, assignment 2, assignment 3, they are here. Please pick them up if you haven't yet. And assignment 4 solutions would be posted right after class today, and the graded homeworks would be available later in the afternoon today for you to pick up. Okay, so this is going back to. So I want to do a kind of a concise review of the topics, and hopefully we also get a feel for numbers, and so that you know that if you're calculating something way out of where it should be and all that, to get a feel for what numbers are and such things. So if you go back, we talked about, in the course in the beginning, we talked about how light beams propagate, what is the shape of a light beam. It's Gaussian, or it has multi-modes, or things of that nature. But in chapter 6, we started talking about optical cavities, right? And specifically resonant optical cavities. And by now, I think you have solved enough problems and looked at enough situations that we should be very comfortable with what that is. What is a resonant optical cavity? And the idea of a resonant optical cavity, this is just a sketch, but it could take many forms. You could have 5 mirrors, 3 mirrors, ring cavities, or this is a linear cavity, if you might, right? You have all kinds of cavities. But the main idea of a cavity is every mirror has a certain reflectivity, right? Which tells you that if this is 0.98, that means if 100 photons hit, 98 go back and 2 go through. That's the meaning. That's the meaning of the reflectivity, right? And so based on this, we can see that if both of them were 1, then it would be a perfect cavity in some sense, but actually it would be useless from the point of view of lasers, because you use that non-ideality to get the light out of the cavity, right? So, yeah. But if the distance is d, then you have a certain number of longitudinal modes of light waves that will fit inside there, right? If that's your wavelength. And it's pretty clear that you need an integer number of half wavelengths to fit inside, and that's really the heart of the idea of the cavity. Repeating it all over again, but that's that. And that leads immediately to a certain frequency, set of frequencies that are allowed, because speed of light is equal to the wavelength times the frequency of light, right? And therefore, from here, because only some wavelengths are allowed, as a result, only certain frequencies are allowed. Which frequencies are allowed? We can write an integer q, and essentially you get 2 times. If your refractive index of this medium here is n, the small n, times d times q. And so the q is an integer. So those are the only frequencies that are allowed. And if I now plot it as a function of frequency, I get only these discrete modes which are allowed. These are longitudinal modes, meaning what is longitudinal? If the light wave is going this way, that's longitudinal. Anything that happens in the x or y here transverse are transverse modes. So these are the longitudinal modes because of longitudinal cavity. If you have some other cavity effects in the other two directions, which we'll see later in semiconductor lasers you do, then you'll have those control transverse modes. But this is the longitudinal. Okay? And so what we are saying here is this frequency is your C over 2nd times this integer q, and clearly the separation is q plus 1 minus q. The separation therefore is just a C over 2 times nd, because these are integers, right? So, and that's your free spectral range, or FSR, right? And just as a calibration, again, the frequency of visible light typically is frequency of visible light would be of the order of 100 terahertz. Depends on the wavelength and the color and other things. But these are much smaller. Okay? These are typically in megahertz or gigahertz, depending upon the size. Right? This is right. So essentially, what we're looking at then is I have light. If I start out my axis, it goes all the way somewhere far out there. That's 0, and then I have a center frequency somewhere nu0. But it's saying that if I have light of that wavelength, only certain will be allowed nearby, and not all of them will be allowed, right? So that's the cavity idea. Right? Okay, so just again, of the order of gigahertz. Again, I think we understand that we can control it by changing the distance and the size of the cavity and such things. Now, if the reflectivities were infinite, then if reflectivities were completely 1.0, then none of the light would get out. But if reflectivities are like such, then we can ask the question that what is the if I have light inside, what is the transmission coefficient, meaning how much of the light gets out of the cavity as a function of its wavelength or a function of anything like that. Does that make sense? I mean, that's the transmission function that I can plot. I think you can see from here that if there is cavity modes that are not allowed, then there's nothing to transmit. I mean, the only ones that will really transmit are the ones that are allowed. But then what happens here is because of the finite reflectivities on the both sides, and I'm not trying to derive this. Essentially, one has to now see, you get the round trip travel time, right? The tau round trip is very simple. Speed of light by 2 times nd, right? Total distance divided by speed of light in a material with refractive index n is just c over n, right? So that's your round trip time for travel, and which is, as you can see, directly related. It's 1 over this FSR. So the reflectivity as a function of frequency, if you might, would be, and this is something that you can write down by following the electric field profile as it goes through and coming back and saying that, if I keep adding all the reflected waves here essentially see how much of it is retained inside, 1 minus that is how much of it gets out, right? And that obviously now depends on frequency. And what you will see here is you get something like this: 1 minus R1, 1 minus R2. And this is again an expression for the total transmission, and then what you get, like 1 minus R1, R2, something of the sort. Again, sine squared frequency. All right. And then there's 2 over c. No, what was that? No, there's a distance here. No, yeah. C. No, this should be dimensionless, right? So I should get a c here. D. Something like that. Right? So yeah. I just want to make sure I'm not writing it wrong here. theta is 2 pi d over c. Yeah. Sorry. All right. So now you can make a plot of that thing, and you'll see now that it looks, like that, right? That's your how much light can get through, and there's a little bit of a broadening. You can ask how much is the broadening in the transmission function. I'm plotting now how much light is getting out. Transmission as a function of the frequency. So first of all, the FSR that's allowed, the modes that are allowed, and then it just because of reflectivity and there's a slight amount of broadening in this situation, and you can ask now what is the broadening? How much is this little thing here? And that's labeled as delta nu, full width half max of frequency for the transmission. And that will come out to be obviously related again to the reflectivities. First of all, you can see now it should make sense. If you put reflectivity is equal to 1, this is 0, you'd have no transmission. If your reflectivities are high, you have a lot of transmission. So that's, a lot of it leaks out, right? And the broadening would be, it's a frequency, therefore you can kind of almost blindly here write down, there must be a natural scale of frequency. What is a natural scale of frequency? Well, it's the FSR. It's a natural scale of frequency. The broadening is a fraction of the FSR. Right? So what fraction? Let's first write down the FSR. That's just that, right? That's the FSR. And the fraction happens to be, there's again, I think you can, this is only if there's reflection. Now very soon we're going to put a gain medium inside. There'll be a couple of transmission hits here. So this will, instead of R1, R2, there'll be some transmission, reflective, other losses as well. But if you have just mirror losses, then it looks something like this. Okay, R1, R2, and I think it's in your, again, derived or all this stuff in your book here, 1/4 or something like that. That's your line width. If you, all right, so this is your full width half max of the reflection, so of the reflection. Yeah. And now you can define what you call as a quality factor, and we'll just make a physical connection to the quality factor. The quality factor is essentially your center frequency, the center frequency divided by the full width half max. Right? That's the quality factor. Let me just write that down, and we have I think we just, quality factor would be whatever is the center frequency divided by this whole thing. And center frequency is basically this. No. Forget about what I just said. Center frequency is whatever it is, and then you, use this quantity here, C over 2 and D, and just turn it upside down. I don't want to write the whole thing, but quality factor is dimensionless, and it's the center frequency divided by the width. Yep, there's a question.
Is the transmittance that you have up there for both sides of the laser, or just one?
Total, meaning how much energy is leaking out the entire cavity. This energy plus that energy. Okay. Yeah, right. It's a total. So, yeah. The way you get that is you get 1 minus what stays inside. Now this is all outside. Right? So quality factor is that, but I think if you remember, Cliff had mentioned that this is kind of not very fair because you are dividing a huge nu naught, right, which start from 0 there, 100 terahertz something, divided by something which is giga. That's not very fair. A more fair quantity is what is this width divided by FSR. That's more fair, and that's called the finesse, right? Finesse, just definitions, but finesse would be FSR divided by this. That's a little more, makes a little more sense for the laser. And if you do just orders of magnitudes for these quantities, we just talked, this is 10 to the power 14 hertz, 100 terahertz. This is gigahertz, 10 to the power 9 hertz. So immediately you get a quality factor of 10 to the power 5, easily into the million sometimes, or a billion sometimes, if you have a good cavity, 10 to the power 9. But the more relevant quantity here is this, which is of the order of 500, just a rough guess for some tabletop lasers. Finesse is about 500 because you're dividing, you're starting with a smaller nu naught here. So yeah, you had a question.
So how do you find the ratio between the transmittance that goes from one of the mirrors to the other mirror?
I'll just say that the total Remember, we have to be a little clear about what is transmission. Transmittance of 1 is 1 minus R2.
Okay, it's just
That's that. There's nothing else. But then if you combine the two and there's a wave inside, that's why you get that. You see, I mean, if you had only 1, that's your transmission. Yeah, that's the transmission. There's none of this anymore. Right? Put R2 is equal to, I don't want to say that, put R2 is equal to 1, but that's effectively the way to think about it. But the moment you have 2, it's now mixed up. You can't just put 1 to 0 and so on.
So yeah, my question was that. So once we have a wave, how do we find the ratio of the transmittance of like that's leaking out on one side of the mirror to the transmittance that's leaking out on the other side of the mirror? With the wave.
Right. So you're saying how many joules would come or watts would come out here, yeah, and plus here. All right, let me just defer that to some other time, because it's if you did not have this mirror, obviously this would be the case, yeah, right, and so on, and that part is a ratio of R1s and R2s, as you can see, right. You can put R1, the larger it is on one side, if reflectivity is larger here, more power is coming out there, so you can kind of back out from there how to calculate it. I'm saying that we can defer that for some other time. So, not now. Yeah. All right, so these are orders of magnitude. Reflectivities are typically for very high, good mirrors in, like a physical mirror plate. It would be of the order of 98, 99% or more. But for semiconductor lasers, the reflectivity is actually much smaller, typically about 30%, because we use 30% because we typically use these cleaved edges as a mirror, just a cleaved crystal face as a mirror. So it could be 30%. So, yeah. Now, if you add gain into this medium, which is the heart of the laser, right? We add gain because you're losing photons, and the moment you add some gain into this medium, that transmission coefficient gets slightly modified. You get a gain term here, you get a gain term here, and you get a gain term here, slightly modified. And then now you can basically have more light. So physically what would happen now is if I add in a gain term, every time I get a pass, there's an amplification of the light. So you can have now, so the only way to add a gain term is to pump this medium, create population inversion, and so on. And so the P out would be related to P in, which is the input power, and you can now get a steady state gain, and that's kind of the idea for the next topic I want to cover, which is where's the origin of that gain. Okay. Couple of things. We can kind of define losses instead of saying R1 and R2. We can kind of say that, let's forget for a second the gain term again, a distance d, we define a loss per unit length. Imagining I don't have mirrors like that, I actually have a uniformly lossy media, let's say, right? Then what is my loss per unit length? Right? So if the wave is going through, that's actually rather straightforward. We say that, well, total loss really is R1 times R2 here, right? And then I'm going to say if I had a uniform loss, you know that light intensity changes with distance as e to the power alpha z. If I have loss, and we add alpha, and then we have 2 times d here, and I equate to that, and that's my prorated loss coefficient per unit length. Does it make sense? It's very simple. I mean, we are not really defining anything physically new. Just saying that if I had a uniform loss, then I know my intensity is going to build up, because loss uniform loss means something like this, minus alpha rate of loss. So you got e to the power minus that. So and alpha from here you get that the loss coefficient will be 1 over 2 times the cavity length, natural log of 1 over all the losses combined. If I have some other losses, just keep adding them, or putting them all in. Typical orders of magnitude, if your reflectivities are about 99% or so, you get natural log of a relatively small number. There's a distance sitting here about maybe a meter if you have a large laser, maybe a few, I don't know, let's say 5 inverse centimeter, order of magnitude. order of magnitude. Obviously, in a semiconductor, what would happen is this would be very small, but so would these would be very small. So it kind of balances out. This is roughly where you would get. If you're down in the trenches, if a really bad medium, very inhomogeneous, very defective medium, it can be very large. And then, good luck with lasing. You probably won't. But now we must have gain to overcome this loss, right? And that's the idea of now stimulated emission, which is the chapter 7, atomic transitions and all that in your book. Okay, so yeah.
So if we had a gain medium over there,
Yeah.
would the gain medium show up in the numerator of that natural log term?
We'll do that now. The gain medium will show up as here. So this is the total. We'll see now that excuse me, gain coefficient and loss coefficient. That's how it's going to be, right? So, and that won't be the whole story. Since we are at it, might as well finish the whole story. We'll see that we cannot keep getting as much gain as I want. There'll be at some point something called a gain saturation, and that's really your main way it works. You cannot keep amplifying signals because when you create population inversion, there is a certain limit, and now you want to, when you're getting gain, you're losing your population inversion, so your gain starts collapsing, right? So that's this thing will explain that now. Right? So let's move over to how do you get gain in the medium? What materials should I introduce? And that's where we went back a little bit historically and looked at Planck's blackbody radiation formula, which motivated Einstein to explain the three processes, which is spontaneous emission, stimulated emission, and absorption. And by only after parsing all these light matter interaction into these three processes, one could conceive of an idea of a laser that you could actually get optical gain. Right? And the experimentally, again, late 1800s, people had measured many times the black body's spectrum as a function of frequency. What it really means is at any frequency, how many photons do I have, how much energy do I have in light, right? And the formula always used to, this people knew you could fit it, and it looked like 8 pi, what was that, nu squared over speed of light whole cube times h nu over kt minus 1, right? So that's the famous Planck's blackbody formula. But before Planck, people were unsuccessful in explaining it. They had measured it, they had fit it, they had found out a constant sitting here, 6.6, Planck's constant. They had obviously speed of light, but there was no explanation. And the explanation initially was if I have light that's inside a black box, so our cavity that we just talked about, let's close it on all sides, x, y, z, close it on all sides. It's a closed cavity now, and a cavity which looks something like this, right? And light can only, go back and forth, bounce back and forth this way, that way, and this way, right? X, y, and z. So once you take that into account, you have basically longitudinal modes along all three directions now, right? So you get a FSR of this whole big cavity now, right? And what is that FSR? Now you have a three-dimensional FSR. You have a x directed integer, y directed integer, and all that. So you get all these modes that are allowed, and they are discrete still. And that's your FSR along the x direction, right? FSR along y direction and z direction. So you get all these discrete grid of points in the 3D space, which are your allowed modes instead of the lines that we just sketched there, right? And now you can ask, these are all allowed modes, which ones are occupied, which ones are unoccupied. To detect it, what are we experimentally measuring? You have a little hole here, and you have, whatever light is coming out, you measure with a spectrometer, and say how in this many photons are this, and then this is how you generate this, right? And the main thing here is this box is made of matter or atoms, is sitting at a temperature T, right? At a temperature T. And that's the T that appears here. So the light that's inside the box and you're measuring outside, and the matter are in thermodynamic equilibrium with each other, right? And so the light has an imprint of the temperature of the matter it interacted and got out from. Does that make sense? So that does that. And if you find now how many states are there, so to find out or explain the blackbody radiation spectrum, the idea was I'm going to first find that at any mode nu, which has a frequency nu, or in other words, an energy h nu, right? How many modes are there at that energy? That's the first thing to find out. How do I find that? Well, I go back to that picture, and it's a completely geometric problem. You go out a radius of nu from the center, right, of the sphere, and then you draw a sphere, right? And so you know that on the sphere, all of them have the same radius. Obviously, I mean that's the definition of the surface, right? And so the number of points that fall on the surface of that sphere is what you would call effectively your density of states. How many states do you have at that frequency, right? And the way to find that, obviously you can see that it will go as square of the radius because the surface area increases as the square, right? Square of the radius. Right? So it will increase as the square of the frequency of light, and the density of states, I'm just going to write it. I don't think your book uses this notation. Is yeah, you can go here and find a little skin around it and all that, but I think we went through this earlier, so I'm going to just make use of it here. You go as I'm going to assume refractive index of 1 for argument's sake here, but this is how it's going to increase. It's a very, very, very simple formula. And if you go back and you see that's sitting right here in your really experimentally measured thing as well. So the density of states of light, obviously you can emit into a mode if it's there, and the more the number of modes, the more it's possible to emit into. So before Planck, the idea was the total energy in any mode would be, so the density of states, if I were to just guess the density of states, is going to just increase like that as the square is a parabola. And before Planck, the idea by Rayleigh and Jeans was every mode nu, I can tell you how much energy is in that mode in this way. This is thermodynamic or classical argument, not quantum. Right? Classical argument is in mode nu, my energy is h nu, right? Or rather, let's forget this. That's obviously kind of tilting towards quantum already. But so let's say the energy of mode nu is just E nu, right? And then the total energy, thermodynamic, classical energy in that mode is how many particles are there, or rather the energy of that mode, if you might, right, times the probability of that mode, and the probability of that mode is e to the power minus E nu by kT, and you take that and you essentially multiply and take an average over all possible. This is the expectation value or the mean value of the energy of that mode, right? That's the classical picture. Right? So if a classical thermodynamics tells you this is the probability, if the energy is E nu, this is the probability of that state, right? Classical thermodynamics from Maxwellian picture. And when you evaluate this is the trivial integral. The answer is just kT, right? That integral is just kT. You can do it in a very simple way, right? And that's basically kT for every degree of freedom. They have this probably classical idea that there's energy, average energy is kT for every degree of freedom. And so the Rayleigh-Jeans law said that, well, to find my total energy now, all I need to do is find out how many modes do I have, which is my photon density of states, known way before quantum mechanics, right? Times the average energy per mode, which is just kT. So this should be my radiation pattern, right? And obviously this was incorrect, but it was not incorrect completely, because it was correct. It completely reproduces this part of the curve very accurately, no problem, right? So you increase the temperature, it will go up here. Decrease the temperature, it will go down, and all that. This part of the curve, no problem, but this part, ultraviolet, it's a catastrophe, right? So that's the name of it, right? So along came Planck and said, I know why you have a problem here. because you are making this assumption that you can have any energy. Right? You cannot have any energy. I'm going to introduce this new concept called quantized. So energy can only be an integer times h nu. It cannot be a continuous variable anymore. Right? What does it mean? In any mode nu here, I can only have a discrete number of photons. It could be 10 to the power 9. It could be 10 to the 9 plus 1, but not in between those two. So it's not a fraction. It's always an integer. It can only come in packets. And that's the only change, really, in some sense. So now I'm not going to make a sum because I have a discreteness. So I'm going to sum. I'm not going to integrate. I'm going to sum it times E nu now becomes n times h nu, right? And again, n times h nu. Sorry, it's a mess of notations here. Divided by probability. I mean, he retains this thermodynamic probability. It just said that the energy is not going to be what you thought it was. It's just discretized now. That's the quantum hypothesis. And when you do that, the answer here is no more kT, but it looks like h nu, which is the energy of photon, divided by e to the power h nu by kT minus 1. So that's the new result. And now if you multiply that thing here, right, the average energy per mode, according to Planck, is that, and you get the exact blackbody radiation curve. So that basically proves that it is correct, right? Meaning there is truth to this assumption. Because it explains experiments, it must be correct, right? So, and just to be clear, before that, I mean, if people had only measured only till here, then everything was correct too, right? So just to be clear, I mean, that's how science develops, that you make new equipment, you probe new areas, and you find things don't fit, and then you discover new laws. And that is an example which has been repeated in history, right? So, okay, so is that clear? Or any questions? All right, so explains blackbody radiation from this picture, just by looking at light and saying that, it is in equilibrium with matter, and that property really appears here. The temperature appears here. So now, about 15 years after this comes Einstein and says that I'm going to rederive Planck's blackbody radiation curve, but in a completely different way. And then that's what started this whole laser idea, right? So let's look at his idea. And so Einstein's idea now is I'm going to not look at the light. I'm going to look at the matter that is producing the light. Right? And the matter is composed of atoms. And the atoms have energy states, meaning electrons in the atom can have energies E1 or E2. And I could have N1 atoms in E1 state and N2 atoms in E2 state. Right? And these atoms are sitting inside my cavity. And then they're talking to the light that may be going through, right? They're talking to the light that may be going through. Maybe I have some atoms with excited state that can spontaneously just emit and produce a new photon or new beam of light spontaneously with no excitation whatsoever. Let me call that rate as A21. It's a rate in inverse seconds, 1 over seconds. Right? Typically, it would be inverse nanoseconds. Take about a nanosecond. So its units is 1 over second. So that's spontaneous emission. Now, it's possible that I have a photon coming in which has exactly the same energy separation as these two, right? Exactly the same. In which case, and this is kind of the most beautiful part of it of this result is he says that, well, it's going to stimulate the production of another photon. And that photon, the rate at which it's going to do that is B21. Right? But that photon will be an exact replica of this photon that stimulated it. Exact replica. What does that mean? Exact replica means going back again to our picture of of these modes. So let's say that photon that came in this particular mode out of like a huge number of modes. It just came in that's one mode, right? Then the extra photon that will be produced by stimulated emission will go into that mode. It won't go into, it can have all these other energies, but it will only go into that mode, the same exact mode. Right? Same direction, same phase. It's coherent with the first excitation. So that's stimulated emission. And when you produce that, you obviously you have a gain. You can see now you have photon gain, 1 coming in, 2 going out, right? So you have gain in the photon number. So then you increase the photon number. So you might have been losing it in the mirrors, but you recover it here. This is your, in the analogy of a swing, this is where you get the push, right? The kid gets the push, right? The stimulated emission, right? So, and the third process, which is the inverse, the time reverse process of the stimulated emission, is if I have a state here, it will get absorbed. Basically, a photon comes in, 1 photon comes in, nothing goes out because it got absorbed here. So that's the third process, which is absorption, and B12, right? That's the coefficient, 1 to 2. And now you can run through and just rewrite them. And I think this is the genesis of the laser equation. So it's very important to just focus on what it means. And once you draw this picture, it should be very clear what to write now, right? How does my rate change if I put some 10 to the power 12 or 10 to the 15 per centimeter cube atoms in N2? How does that change with time? If I, let's say, so how does it change with time? Well, it's going to decrease because of spontaneous emission. Every time I get a spontaneously emitted photon, it's going to decrease. And this is the rate at which it does it, right? So, yeah. Just to be clear, the spontaneously emitted photon it does not need any photon, present to the atom doesn't need any other photon to be present to spontaneously emit. That's why the word, right? Spontaneous emission. And that photon goes in any whichever mode it likes, right? And there's a probabilistic process, meaning it will, if I count over a billion spontaneous emissions, I have they're completely uncorrelated. It'll go there, go in this direction, that direction. The phase there's no correlation between them. So that's a major difference between stimulated and spontaneous emission. Right? Okay, so once you get that, so you get a decay rate like that. And then obviously because of stimulated emission, you are also going to lose, right, the population, right, from N2. But now this thing cannot happen all by itself. It needs the presence of photons to be stimulated. And that means, what is the presence of photon? That is my photon field, rho nu, right? That's the light that's present in the cavity, that's going around, that's interacting and kicking this around or whatever. So I must have that thing sitting here. Right? It's proportional to how much light is already there. Right? So that's stimulated emission. And finally, absorption is by which you're going to gain N2, and that is, again, the reverse process of that, B12. And you must have states in state 1 to absorb, and it also depends on the frequency. Right? And right, so this is all the processes that can happen, and there's nothing else. There's no other process that is possible, I mean, in that sense here, right? So, and that was Einstein's picture, and said, now the question was, what happens in steady state? It goes to 0. Right? Steady state, nothing changes. This reaches steady state. And then I can write this expression down as N2 over N1, right? I can rewrite this and get an N2 over N1 here. And from the steady state, d over dt is 0. If I put N2 by N1, I'll get some ratios here. Let's see, you get a N2 over N1, you get like a B12 rho nu over A21 plus B21 rho nu, something like that, right? That's what you're going to get. And now, if these atoms are in thermodynamic equilibrium with the, with the light, the atoms have certain temperature. They're also colliding with the walls of the cavity and all that. If they're in thermodynamic equilibrium, then obviously this thing is just e to the power minus h nu by kT, because if you have N1 and N2 here, then the energy difference this is your thermodynamic equilibrium, right? And from here, you can recover what is rho of nu, and that should be exactly equal to Planck blackbody radiation formula, right? From there, you immediately recover what is A12, B12, all that stuff, right? Because Planck's blackbody radiation, there's no unknown at all, right? It's frequency, speed of light, and all that. But a laser is exact opposite end of this thing, because in a laser, if you have equilibrium, you cannot have laser, right? Because you remember, you can take this temperature all the way to infinity. You get e to the power minus a very small number, that's 1. And the best you can do is N2 is equal to N1, So no population inversion, right? So laser is effectively when you have negative temperature, effectively if you want to think of thermodynamic equilibrium. But that's the wrong way to go about thinking about the laser because you're way out of equilibrium. Right? So that's, okay. So, now comes then, basically what I'm trying to get to here is B12 and B21 can be written just as A in terms of A21 times some other stuff here, right? And this whole rate equation can be rewritten in a slightly different way. But before we do that, there's one little tweak that one has to apply above what Einstein introduced, and that's the idea of the line shape, right? When you actually experimentally measure this spectrum that comes out of here due to an atomic transition, just one kind of atom, let's say, and it's in a cavity, let's say, and you're measuring the energy or the frequency, and you see that, well, I'm expecting, if it's an atom, I am expecting an extremely sharp transition with a frequency of E2 minus E1 over H, right? Extremely sharp. We are not talking about black body radiation now. We're just saying there's one atom. That's all there is, and it's emitting. We expect this energy now, right? And we're going to talk about far out of equilibrium situation because that's the situation in a real laser. And then when that happens, when you actually do the measurement, you see that it's not quite like that. It's, there's a certain amount of broadening here. And for single highly pure species of atoms and all that, you typically see that this is a Lorentzian, and you would actually, this can be derived as well. You would see that this shape of this is a Lorentzian with a certain full width half max over a certain center frequency plus a full width half max again, right? So that's a Lorentzian, broaden. The integral of this whole thing over frequency is always 1, right? But it's a shape which was a Dirac delta, if you might, and it just gets broadened. And this broadening is actually inevitable, even just from the fact that there is a spontaneous emission lifetime. This, if you remove all collision defects, there's always a spontaneous. It takes a finite time for it to emit spontaneously. That already limits what is that line width. When I say this way, it's extremely sharp, by the way. I mean, remember, this center frequency is in 100 terahertz for visible light. And this thing we are talking about, it could be very sharp. It could be kilohertz, if you might. It's very, very sharp. But there is a broadening, right? And this broadening plays a very big role in the laser because the height of this, you can have a broadening which is like that, or you can have a broadening which is like that. The height of it is going to be your gain in the end. Proportional. The gain would be proportional to the height of that. So less is the broadening, more is the gain. That's kind of the game here, right? So that you can have homogeneous broadening, or you can have inhomogeneous broadening. Inhomogeneous broadening is when I have, a simple way to look at it is maybe I have like 10 different kinds of atoms. They have slightly different, homogeneously broadened spectra and slightly different numbers. I add all of them up, I get inhomogeneously broadened spectrum. That's one way to look at it, inhomogeneously broadened. Or you have like a Doppler broadening where a light going this way, but the atom was moving this way thermally. So as a result, you get, Doppler shifts of the emitted light, either get slightly larger or smaller depending upon how fast that atom was moving, right? Just like the police car and the siren that you hear, right? Same thing, frequency shifts, right? And then center frequency shifts and all that. So those are two kinds of broadening, but the end game of all that in the laser physics is this should appear here, right? Because it's not a atomically discrete transition, and I must introduce this frequency dependence of the transition, optical transition in this equation itself, right? And then and now basically we are close to the end of this picture now, because once we realize that we must have this line shape sitting here. This is obviously 1, so that it doesn't really do anything here, but these two now start interacting. The radiation field and the line shape start interacting. One builds the other. I mean, basically, the line shape has nothing to do with the light at all. It's completely a property of the atoms that are sitting in the gain medium. Whether or not you population invert or you are in a loss situation, it doesn't care. Line shape doesn't care with what light there is. Does that make sense? It's just the property of the matter, right? And when you try to build a laser, the light and the matter are talking in this way, right, to each other. Right? So the line shape is talking to each other. And then you redo this equation, and you trade off your B2s and B1s using the Planck blackbody formula. And what happens is you can rewrite this equation again as a laser rate equation, which is I think probably one of the most important parts of this course, at least. So you get this minus. I'm going to just rewrite it, and then we'll go through the explanation of all these quantities. And I think one of the things I have skipped here is you always have this degeneracy factor. I'm going to just write it here, but I'm at this point not trying to describe it. Okay, plus let me just let's call it spontaneous emission here. Okay. So that's your real final laser rate equation, right? And for two-level system. And what it's saying is if I have states in N2, they can either spontaneously decay, or if I have a situation, here are some quantities, it can depend on the ratio of N2 and N1 here. Yeah?
So I'm confused because I thought the first term, A21, N2 was spontaneous emission, so I said it twice.
Oh, no, you are right, Stephanie. Sorry about that. What I was saying, yeah. Spontaneous emission. That's right. Yeah. And this thing is everything else. So you're right. I mean, that's just that term. Thank you. No, yeah. And what I was trying to add there is I may have situations where, this atom is hitting something else and it's losing the energy without emitting light. That is a loss mechanism, non-radiative recombination. That's what I was kind of adding there. At this point, probably it's not, but there may be a loss mechanism, meaning all these three processes we talked about actually either absorb or emit light. But if you look at a semiconductor, you may generate heat. You may collide with the lattice, generate phonons, and not emit light. So you can have a loss term here, is what I want to say. Thank you. It's not spontaneous. Spontaneous emission is here. Okay, so what are these quantities? From here, if you kind of look at these equations and you kind of parse through them, you'll see that, let's look at the intensity. I nu would be inside the laser, your radiation field is quite different from the blackbody radiation curve. The radiation field inside a laser is very, very sharp, right? It's it's the furthest away from a blackbody radiation, and the center frequency, and maybe it has some broadening. And the line width so this is the rho of nu inside a laser. Blackbody radiation, that, laser this, right? And that thing would be, you can pretty much write it as a delta function, as a function of frequency, as a function of center frequency. And so all the energy is combined here, and if you take this and you multiply this energy density with the speed of light, that's how fast the light is, the laser light is moving around, and that's just I nu. That's just a magnitude of that light, it's intensity of the light. Sigma is your gain cross section. It's dependent on A21, obviously, because we have, it's a mixture of B's here, and it depends on wavelength, refractive index, times the line shape. That's what appears here. See, if I choose a Dirac delta, plop that in here, it pulls out the, it just leaves the line shape. Sorry, I plop it into the photon field. I'm left with the line shape, so that appears here. That's your absorption, or this is the gain cross section, or just the cross section, just the cross section. And photon energy, and everything else is straightforward. I mean that N2 and N1 are, it's clear what they are. Number of atoms in state 2 and state 1. Just orders of magnitudes. Cross sections are of the order of 10 to the power minus 12 to 10 to the power minus 20 centimeters square, order of magnitude. And these N2s and N1s really depend on what kind of material we're talking about. Could be of the order of 10 to the power 15 per centimeter cube, or something else, some of that order. Yeah. And then when you look at this equation and say that, well, how does this reach steady state now? And that's where we get our gain and loss idea now, that I can, instead of writing it in terms of N2s and N1s, I can write it in terms of the intensities now, right? And first of all, you can see if I reach steady state, I take that to 0. Typically, this term, at a low intensity of light, this term, well, they will reach equally, equal numbers, and then you can find out what is N2 and N1 from there, from steady state. But if I were to just slightly change it and write it in terms of intensity as a function of distance. So I have this sort of a situation going on. I have light coming in, and I have stuff coming out here. So I can write, and I have N2 minus N1 somewhere in, which may be changing inside here, let's say, changing inside here, right? Then the intensity is also changing inside the gain medium as a function of Z. Get a lot of time. And what we define here is, if I write it in terms of the intensity instead of the number, N2s and N1s, I get a slightly modified equation. I mean, obviously this will go away. We'll see I over H nu will go away, and I'm left with a gain cross section times N2 minus G2 over G1, but I'm skipping that for now, times N1 times the intensity at Z. That's your gain or gain equation as a function of distance now, not time, but with distance. How does intensity change with distance? And the other thing here is, so as a result, this is what we define as the gain coefficient, right? Gain coefficient. But just to be very clear, this thing is what would call as a small signal gain coefficient. What do I mean by that? Small signal means that I think we also realize that every time I have a stimulated emission process, I'm losing N2 and I'm gaining N1. So as a result, this factor is going down. So the gain is going down, right? And you can increase your excitation, but at some point you will reach a saturation because the gain is also coming down, right? As your intensity of excitation is increasing. Therefore, that fact is taken into account. And if you solve your laser rate equation taking into account this reduction of the gain, what you end up getting here is a very simple, kind of picture. You get in the denominator, you get something like that. Right? So it kind of saturates. So intensity is sitting there and also there. I think I'm a little out of time. So when I try to plot this now, you can solve this equation again, and then this is your small signal gain, gamma naught, order of magnitude 10 to the power 15, 10 to the power 15, let's say, and 10 to the power minus 15, inverse, about 1 inverse centimeter could be 10 inverse centimeter. Obviously, if this is no more than the gain, you won't laze, right, and things like that, order of magnitudes, right? So, and when you resolve this thing, you get that this thing will look like this, right? Natural log of I out over I in is equal to integral of dz times sigma, right? So okay, so that's your, if your output intensity and input intensities are both much smaller than the saturation intensity, then you can neglect this and you just retain that, and you get your linear term that, or rather, I out is e to the power gain, gamma Lg, if you might, times I in. So you get an exponential gain. So this is why this is called a small signal gain. If your input and output intensity, if the output intensity is very close to input intensity, meaning you haven't gained much, in which case this term is 0, log of 1 is 0. And you just that, you have only linear increase. So that's a large signal gain when you get gain compression, meaning your photons, your electric field, if it's too long, your electric field was getting amplified initially, but after some time it's not going to get amplified, it's going to just get compressed now. So that's the gain compression, or rather, gain saturation. And we can kind of end here, I think, a little bit over time. But we didn't talk about the dynamics. That's not a part of your prelim, but that's something we have already covered. But this still here, I hope you know this. Look at the problems at the end of the chapters. Solve the ones that were not assigned, some of them. And I think I didn't assign a gain saturation problem, so just look at them also. And but in general, this is the basic idea of the laser that we have covered till now. Okay, thank you.